Welcome to Chapter 10, and we'll be talking about electrophilic addition. This is a new mechanism, EA, electrophilic addition. And for these, an alkene will be your starting material. That's your functional group. And then you can go to lots of different functional group transformations depending on the different reagents. And you're going to see that the mechanism, and we've talked about mechanisms, we've talked about acid-base reactions, we've talked about SN1, SN2, E1, E2, and now we're going to talk about EA, electrophilic addition. And your starting material for these are alkenes. Your starting material for SN1, SN2, E1, E2 was an alkyl leaving group. So we're talking an sp3 carbon with some kind of leaving group attached, lots of times a halogen. Acid-base reactions, you have to have an acidic proton and then a base, which has to be either a lone pair or a negative charge for a strong base. And then you look at pK values. So these are so far the different reaction mechanisms and reaction type classifications you are expected to be able to draw the mechanisms and then predict products. And so now we're going to go with electrophilic addition, and you'll see that the starting materials are going to be alkenes. The next chapter is still electrophilic addition, and instead of alkenes, you're going to have alkynes, which is a triple bond starting material. And that will be chapter 11. And then that's where we're at this point. Okay, so we talked about alkenes and we've talked about which ones are the most thermodynamically stable. So this is a review. This one is di-substituted. This one's tri. You see there's 3 groups here. Here there's just 2 groups. Here this one's di. And also, so we got di. This is a terminal, meaning it's at the end. And this is an internal. So an internal is going to be more thermodynamically stable than a terminal. And then this is also a di. And so if you're choosing between these two, this one's a trans because you have the higher priorities on the opposite side of the alkene, and this is a cis. So we know that trans is more stable than the cis. And the cis is going to be more stable than a terminal because this has no cis-trans isomerism. So we can say D is going to be greater than C, which is going to be greater than A, but a tri is going to be greater than all. So which alkene is the most thermodynamically stable? Hopefully you can choose B on that. Okay, like I said, we're in chapter 10. We're going to be doing electrophilic addition. So alkenes are going to be our starting materials, and they're also called olefins. A terminal alkene will have a double bond at the end, so this is a terminal. These are internal, and this is an example of a cycloalkene. These will all be cis, and you'll see that you have to get 8 carbons or more for a cyclic alkene for trans to be stable. Okay, so 7 or less, you're not going to have any stable cyclo compounds. Hybridization is an sp2. It's an sp2. There's 1, 2, 3 groups. The superscripts add up to 3, and we know that's 120 degrees, and it's planar, so it's flat. So it has a top and a bottom. This is showing you cyclooctene, so that's 8 carbons, and that's the first time you can get really a trans. So this is a trans. This is an example of a cis, where these groups are on the same side. So cycloalkenes having fewer than 8 carbons have cis geometry, and that's why you don't say cis. on a cyclocompound in the naming. So the trans-cyclooctene is the smallest isolatable transalkene, but it's still less stable than the cis-cyclooctene. So there's restricted rotation when you have a carbon-carbon double bond. Same thing with the cyclocompounds. And so that's why we have different diastereomers. Here's a trans and a cis. So you have these groups on the same side or opposite side, which makes them trans. These groups are on the same side, which makes them cis. This is a terminal alkene. So to name alkenes, you have to go through the alkene. So when you name it, you find your longest chain, you have to give it the lowest and you have to go through it. So this would be 1-ene and so this is hept. 1, 2, 3, 4, 5, 6, 7. So that's hept 1-ene and then 2-ethyl. And you don't do cis or trans here because this is a hydrogen and a hydrogen, so there's no cis trans. You see how this one does not include the double bond, so you have to actually contain the double bond, and it needs to be lower numbers if it's your highest priority of functional groups. This one here, you have to do the longest chain. You got to include the double bond, but your numbering is going to be 1 because alcohols have a higher priority than alkenes. So here we do prop 2-ene 1-ol, and the 2 is the starting carbon that you go through for your alkene. Here, 1, 2, 3, 4, 5, 6, 7. So there's hept, 6-ene, 2-ol. And you don't have cis or trans here because these both have hydrogens, which are the same thing, so no cis-trans isomerization. Okay, so when you're naming cyclo, you got to have cyclo, and you got to go through that double bond. So 1, 2, 3, 4, 5, and you want to give it the lowest number. Here, you notice you start at 1, and then you've got to get to the substituent, and you're going to have to go through that double bond. So that puts it at a 3-methyl cycloheptene. And you don't have to give the number because it is known that you would start at the 1. So here, you can go clockwise or counterclockwise, except you have to go through it. So that gives the substituent 1, 2, and so there you get 1,6-dimethyl cyclohexene. You have to do cis and trans if you have cis and trans. So here, the priorities are the same. Carbon is atomic number 6. You can draw your hydrogen atomic number 1. So this would be between those, this would have a higher priority. And then you would come over here and look and say, okay, carbon is 6. We have a hydrogen there, which is a 1. And so this is your number 1 priority because you're just doing 1 and 2. This is number 2, number 2. And then since the higher priorities are on the same side, that's cis. Here you look at this carbon and you say, okay, that's atomic number 1, this atomic number 6. This is a number 1 priority. This is a number 2. Same thing here, dealing with 6 and a 1. This is a number 1. This is a number 2. Where are your number 1s in relation to each other? They're across from each other. They're opposite sides, so you have to put trans. Now, cis is also Z, so you could see the Z or E. So this is just showing you like to sign up priorities. You do the priorities just like you did before. You see that the 1 is on the opposite side, so that's going to be trans. So when they're on opposite sides, they're going to be the trans. You see the E in parentheses here. If they're on the same side, then they're going to be Z. Common names, this is a methylene, a vinyl, allyl group. So and you've probably already been introduced to that. which is the Z. So you need to know Z is cis. I think of E.T. Phone Home, the movie. E is trans. So Z, this has no, because this is a hydrogen and a hydrogen. So if you were to name that, it would be 1, 2, 3, 4. That would be 2-fluoro but 1-ene. This one, this is a carbon, which is 6. Fluorine is, I want to say, is it 8? 1, 2, or 7? It's 7? Oh, well, I don't have a periodic table, but it's the higher. So carbon is 6. What is the atomic number for fluorine? Okay, so this is number 1. And then bromine, you know, I do atomic mass because that's old school. This is the heavier, so this is the number 1. This is number 2. So number 1's, this is going to be trans, or you could say E. And then it's butene. So 1, 2, 3, 4. So 2 bromo, 3 fluoro, but, 2-ene. And for my open responses or anything like that, as long as if you did these numbers differently in this situation, as long as I could go back and forth from structure to name, we would be okay. Here, between fluorine and carbon, this is number 1. Between fluorine and chloro, that's number 1. So this is obviously cis, and cis is Z. So we have Z, and then 1, 2, 3, 1, 2, 3. So that would be 1, 2 difluoro, 1 chloro, and it's propene. You could put the 1 in there if you want. Okay, so that's obviously cis, and I think that's what it's asking for. There's C. You can look at this one here. This is number 1. This is the same thing. So this has no cis trans isomerism. Okay, physical property of alkenes. They intermolecular forces. They're going to be weak. They're going to be van der Waals. So these are going to have the lowest boiling points and melting points. They're also going to be soluble in hydrophobic nonpolar solvents. They're going to boiling points and melting points will increase with the number of carbons that are increased, because as the molecular weight increases, the van der Waal interactions increase. Cis and trans differ in physical properties. Okay, so here, this was one of your quiz questions, and you're going to come up with it. Assigning dipole. So you see that there's no symmetry here. These are electron donating groups, but the overall dipole pushes, and these are weak, but it's something to be said. You do have a dipole. The dipole, which is this cursive U, is greater than 0 dBi because there's no symmetry. This one, since there's symmetry, this is 0 dBi. DE is just the unit to measure the dipole. So when you have cis, you're going to have a net dipole. So this is going to be more polar than the trans. And you're going to see this in different physical properties. Physical properties mean melting points and boiling points. So cis butene has a higher boiling point, 4 degrees Celsius higher than trans. And it's because it does have a little bit of a dipole. So ethylene is actually a ripening agent. So if you get like green tomatoes and you pick the tomatoes, so that means they're not ripened on the vine, and you put them in a truck, and then you get your tank of ethylene gas and you spray them, they will all turn red. And then you can put them out on the shelves when you transport them where you want them to be, like a Kroger or something. Okay, so this is a ripening agent. Plants give this off. So if you put bananas next to each other, they're going to give off this ripening agent. So if you ever wondered. But anyway, ethylene is the precursor to many uh, stuff like PVC. You've probably heard of PVC plastics, the polyethylene, ethylene glycol is your antifreeze, which is very poisonous and toxic. Styrene, styrofoam, paints. So there's a big market for that. Beta carotene, orange pigment. So we're talking, these are, we call this conjugation. It's a new word. It's an alternating double, single, double, single, double bond. These alternate. And if you get enough conjugation, you can get it into the visible color range. So orange, we can see this. And this is how you get color in organic molecules. You see these are all sp2, 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 sp2. These are all sp2. And that's what happens when you have this alternating double single bond. This is an example of an alkene. This has 3 double bonds. This is not an aromatic, okay, because it's not fully conjugated ring. So oil of ginger. So a lot of your vitamins they're colored, right? And you get them like in carrots, and they're going to be these organic alternating conjugated double bonds. Lycopene is the color for red for tomatoes. This beta carotene is a pigment of orange. Okay, fatty acids, these are groups. So a fatty acid is an ester. Do you see this is a triester? So this is an ester group, this is an ester group, this is an ester, and the backbone is this triglycerol. Okay, so that is the backbone in which these esters, these R groups, then are going to be your 11 to 9 carbons, and you're going to see that you have saturated fats and unsaturated fats. And unsaturated fats have these double bonds, okay, in their big long carbon chains. And you see them like this. And then unsaturated fats, and they're typically like a 9 or 11. And so you typically get something like this. And you'll see that this is cis. Okay, so plants have these cis double bonds in their long fatty structure. Saturated fats are like fats, like animal fats. So animal fats have saturated, they're like Crisco. They're going to be solids at room temperature, okay, because they're saturated. And then you've probably heard of something that's bad for you, trans unsaturated. And that is, if you get this, is a trans. That's not in nature, folks. That's man-made, okay? That would be synthetic. You get that in margarine, and you get that like in French fries. When you make and cook the French fries, you make the French fries, you get these trans fats, which might be something like that, unsaturated, trans unsaturated. The body doesn't know what to do with those, not found in nature. Not good for you, bad for your human health. So this is showing you the different fats. These are cis, you see. There's 2 of them for linoleic acid. Oleic acid is here. Stearic acid is animal fat. There's none of these. And these are your oils. So you see the melting points are going to be lower, the more unsaturated. This is a melting point of 69, which is a positive. So the larger number of cis double bonds, the more kinks. And this is why there's a thing, it's called structure determines function. Determines function. and that you know this, right? Like I'm sitting in a chair right now, okay? Now, I was asleep before and I was in a bed, okay? Because the bed has a certain structure that helps me lie flat, right? So I'm lying flat on the bed, but then when I get up to work, I need to sit at my desk, okay? So the structure of what I'm sitting in determines my function of what I'm kind of doing, right? Well, same thing with structures. Stearic acid is this Charlie Brown zigzag, and then oleic acid has this kink. It's a bent, and the more bending you have, the less stacking you have. So if you take like, let's take 5 pieces of paper. You take 5 pieces of paper and you wad them up, and you wad them up. Okay, and then you straighten them out. Okay, they're not, are they going to lie flat on each other? As opposed to if you get a ream of paper and then you're taking one and the next one and the next one, they're going to stack better, right? Compared to wadded up paper. And that's kind of what's happening with your unsaturated fats. It's about the stacking and how easily they are to utilize in your Krebs cycle to do combustion reactions for energy. Triacylglycerols, these are just how we store our different fats and oils, and saturated and unsaturated. We've kind of talked about this, so you can just read this. Now, one of our learning objectives is we've talked about alkenes. So we're going to be talking about how you need to synthesize them. Okay, so we've introduced the physical properties, intermolecular forces of alkenes. How do you make them? You need to know that. How do you make them? These are going to be E1 and E2 reactions, folks. That's how you make them. You already know this, so this should be a little bit of a review. And then the new materials, alkenes as starting material. Okay, and this is going to be a new mechanism, electrophilic addition. And you'll have to know different reagents and what functional group transformations occur. So here we have a secondary alkyl halide. So that can go E1 or E2, right? But then we have this really strong base. So it's going to be E2. And so there's your alpha, you're drawing your beta. And you know that E2 has this stereo selective component. This one won't matter, the chair. You'll put in your Br there, and either one of these hydrogens next door are the trans diaxial. So the base can then come in and take any one of these, and you have your beta elimination reaction that gives you your E2 product. Here we have a sterically hindered base. It's a strong base. This is a primary with a leaving group that tosylates. There's your alpha. There's only one beta to choose from, and so with this strong base, it will choose that and give you this terminal alkene. Here we have acid, strong acid. We have a tertiary alcohol. So this is going to be an E1. We call that dehydration. And alcohol is a horrible leaving group. It's got to get protonated first. When it gets protonated, now it's a good leaving group because it's going to be water. And this, since it's a tertiary E1, you got to get a carbocation intermediate. So that's going to be your alpha. So your beta can be any one of these. They're all equal. And this catalyst will regenerate itself by taking the beta hydrogen to make your alkene. And that's always going to be Zatsev's rule, the more substituted alkene. This is an E2 because you're going to convert this alcohol into a good leaving group with this POCl3, POCl, and then that becomes POCl2, but then it generated this Cl minus internal, and there's your alpha and your beta, but it doesn't do an SN2 here because we have pyridine, which is going to act as a base to take that beta hydrogen and give you the alkene. Which of the following alkenes would have the highest boiling point? Okay, well, this is trans, and it has symmetry, so that would be 0 dipole. This also would go this way. Actually, I drew this wrong because these are electron donating groups. So it would go this way. This would pull this way, and it has symmetry, so 0D. This is your cis. Okay, so this would have an overall dipole, and then this one would have this. This is also higher molecular mass, so that's something to think about when you're dealing with van der Waals. So C, because it's cis, so it has an overall weak dipole moment. What is the correct name for the following compound? Well, alcohol has a higher priority, so we're going to have to give that the lowest numbering. 1, 2, 3, 4. We have to go through the double bond. 5, 6, 7. So 7 is hept, and that is, you got to do the 4-ene, and then 2-all. So we got the 4-ene, 2-all, and then what are our substituents? So if we get our substituents in here, we have this substituent, we have that substituent. So the substituent there is 4-fluoro and 5-methyl. The fluoro would come first because it's alphabetical. And then you see that we have trans and cis? Trans or cis isomerization. So let's look at that. Between the carbon and the fluorine, this is going to be number 1. Between the carbon and carbon, we got to go out to the next carbon. So this is number 1. So that would be trans, and that would be E. So you'd have to do E here. And then we also have this sp3 stereogenic center, and what's coming at you is the hydrogen, which is number 4. Oxygen's number 1 priority, and then carbon and carbon, this would be number 2, this would be number 3. So when you do 1, 2, 3, connect the dots, you're turning the steering wheel counterclockwise to the left, so that's S, but then since hydrogen's coming at you and it needs to be in the back, you're going to have to do your flipperoo. So that should be 2R. Okay, so 2R, because that's 2R. So here we have 2R and 2R. We have 4-fluoro, 5-methyl hep 2. So these are all the same. And then is it cis or trans? E. E is trans. So C is your answer. Okay, addition reactions. This is electrophilic addition. This is the mechanism which your starting material alkene goes to. You have 2 carbons that you're going to be looking at, okay? So this is alkene, and this becomes an electrophile. See, at first it's a nucleophile. First it's a nucleophile. You see how when I draw a nucleophile, I put these 2 bonds underneath because it's a source of electrons. So nucleophile is going to go to an electrophile. And then it's going to become an electrophile, and it's going to go to a nucleophile. And this is going to be your typical mechanism. So, and then the reason why it's electrophilic addition is you're going to add the X and the Y, whatever this is, across the double bond. Now sometimes it won't matter, Br2, so if that's your reagent, Br and Br, X and Y would be the same, okay? But sometimes it matters, like if you have HBr, okay? So one of these carbons, and this will be regiochemistry, one of the carbon will get the H, and the other carbon we'll get the Br. And so that's when X and Y don't equal each other. Okay, so they're just showing you, like in a nucleophile, you have this rich electron rich area, and that is initially going to be a nucleophile. Okay, syn and anti-addition. So syn and anti, now you're talking about this stereo selective. Okay, if it's syn, that means it's on the same side. So does your reagent add syn, or is it opposite side? And that's anti. So you're going to also have to pay attention to this. See, your X and your Y added the same side, so that's syn. And then if it's anti-addition, the X and the Y add on the opposite sides. And so when you're learning electrophilic addition reaction mechanisms, you need to really take note whether these reagents do syn addition or anti-addition. So here we have cyclohexene, and these are, see, 1, 2, 3, 4, 5 reactions, and then there's another one that I'm going to make another. I'm just going to go through the other slides. There's for this chapter 10. There is another reaction that I will include in here, and it's mercury acetate, and that would be either in water, and then, or you could use an alcohol. Okay, so you could use some kind of alcohol, but, and then the second thing is the sodium borohydride. So that is a 6th reaction we're gonna include in this group. This one's called hydroboration oxidation. This is called oxymercuration, demercuration. You have a POGL exercise with that one as well. So right now we're going to go through these, and you're going to see the different ways in which these add. So here's the name, hydrohalogenation, because you're adding a hydrogen and a halogen across the double bond. This is called hydration because you're adding water, HOH, water, H2O, across the double bond. Halogenation, you're adding, see, the same thing, bromine or chlorine or iodide. Well, it looks like just 2, bromine or chlorine. Halohydrin, you're adding an OH and a halogen. Okay, so Cl or bromine, and then also an OH. Hydroboration, oxidation, that adds water. And you're going to find that oxymercuration with water also adds water. These make alcohols. So here, if you have HCl, you're adding H and Cl. And so what's happening is this is your nucleophile and this is your electrophile. So you got the first step is 2 electron flow arrows, you see, and then you've got to add the hydrogen to one of these carbons, and then the other carbon will get a positive. Okay, so you'll make a carbocation. And we're going to care about the more stable carbocation. You'll see that that'll determine which, because you want the most stable carbocation intermediate, which one you get is the more stable. And that'll determine the regiochemistry of, does the hydrogen add to the first carbon or does hydrogen add to the other carbon? And then, so this is your nucleophile. And this is your electrophile. So there's your nucleophile. There's your electrophile. And now you've generated Cl minus. And so now the second step, the nucleophile adds to the electrophile. And that's how you get an alkyl halide. So you can add HBr and HCl. And you get, so the functional group transformation is you're going from an alkene to alkyl halides. This is your functional group transformation. And so here's your mechanism. The nucleophile is your alkene, and this is your electrophile, and you protonate the OH, and you get this carbocation, and then your nucleophile is your bromine, and it adds to your electrophile. Notice here we have two curved arrows. Here we only have one. And then this is a stepwise reaction because you're getting a carbocation intermediate. So if you were to do your energy reaction diagram, it would look a lot like the one, okay? Like it would look like SN1, it would look like E1 where you got a carbocation intermediate there. So depending on which carbon, it doesn't matter which carbon the hydrogen adds on this one because they're both symmetrical. They both have only one carbon. So you're going to get the stable carbocation. So this is showing you the reaction energy diagram, and there's your carbocation intermediate, and this is electrophilic addition. Now this goes Markovnikov's rule. You could just say Mark's rule. You might hear me say Mark's rule. That's going to give you the more stable carbocation. So you're going to find that some give you the more stable, okay? And then that would be if you don't get the more stable carbocation, you get an anti-Markovnikov. So, and you might hear me say anti-Mark. So you're going to have to kind of memorize and look for those reagents that follow Mark's rule to give you the more stable carbocation intermediate, or the kind of reagents that do the anti-Mark. So here you have an unsymmetrical alkene. You can see that this carbon here is bonded to a carbon, and this carbon is bonded to two hydrogens. So now when the hydrogen adds, it does matter. You're going to want the carbocation to be on the 2 carbon to give you more stable. So then the hydrogen is going to add to the first carbon, and that gives you the more stable carbocation. Because if you add it to the other one, you would get the primary that the hydrogen went there. And that would be a primary carbocation, where this is a secondary. So this is not formed. Okay, you see the only product here? Because now your chlorine here is going to add to the carbocation to give you this product. That's Markovnikov's rule. And so they're showing you that you don't get the primary carbocation, you get the secondary. And here, this is just the first step. This is step 1. There's 2 steps where the alkene is adding the HCl, and they're showing you that this carbocation, the secondary one, is going to have a lower energy. See, it has a lower energy, and therefore also has a lower activation energy, and this one's too high of an energy. It's not going to happen. So now they're talking about this stereogenic. So when you have this is an sp2 and sp2 carbon. Remember that it's flat, okay? And so when you add HCl, and you get your carbocation as well. So let's see what that looks like. So when you draw your intermediate from the electrophilic addition, you're going to get your so here you're going to get your carbocation there, and the H is going to add to this other carbon. So this is the Markovnikov's rule that gives you a tertiary carbocation. Remember, you always want to classify it, and then the chlorine's going to come there. This carbocation is sp2, folks, so it's flat. It's planar. It has a top and a bottom, so the chlorine can add from the top and it can add from the bottom. And so you get 2 enantiomers. So you get the R and the S. Now, for me, I don't expect you to draw both enantiomers, because if you drew just one enantiomer, then technically you got to draw the second one, okay? Because You can't just say that this is 100%, okay? Because really you're getting 50% of one enantiomer, 50% of the other one. We call this racemic. Remember, it doesn't rotate plane polarized light. I'm okay if you just draw it with a straight line there, because that implies that you do get 50-50. So this is just showing you what I just showed you, the carbocation, and then your nucleophile can add from the top and bottom. So you get both syn and anti-addition, and because it's flat. So this mechanism, this is hydrohalogenation. So you're looking at your reagents or reactants, also known as reagents, or HCl or HBr. And they're always going to add H first, okay? And you're going to get the more stable carbocation, and then your nucleophile will add. Rearrangements can occur, okay? Because anytime you're dealing with a carbocation, you can get hydride shifts and you can get methyl shifts. Markovnikov rule will follow. You'll always get the more stable carbocation. And you can get both syn and anti, so you don't even have to worry about that. The only time you're going to see me tell you to pay attention to this is when you get one or the other. And then we'll call that stereospecific. This is regiospecific reaction. What does that mean? The region in which the H adds to the carbon-carbon double bond, the region, this carbon versus that carbon is a region, and it's specific because it wants to follow Markovnikov's rule. So Markovnikov's rule is regioselective. That's what that word means. What is the major product in the following? Okay, so I expect you to be able to write this reaction mechanism. So this alkene attacks that electrophile. You get this intermediate. The hydrogen is going to add to this carbon here. And then you get a carbocation here. You want to classify it tertiary. Tertiary, if it traded places with the next door neighbor for a hydride shift, it would be primary, so you don't have to worry about rearrangement. And then the BR, it's generated here. We'll add there, and you get a BR there. So that is a tertiary. And this is actually too many carbons here. So this is a typo there. It should be B. Too many carbons. So make that a fill in the blank. Okay, what if we add water? So we're going to add HOH. So one of the carbons is going to get an H and the other one's going to get an OH. And you're going to see in that next slide lecture, it'll be really short because I want to include the reaction that's not in your textbook, but it's in your POGIL. These are, I say that there's 3 ways to make an alcohol, and this is one of those ways. Okay, from an alkene. So we're talking about from an alkene, there's 3 ways to make an alcohol. So this is an alcohol transformation from an alkene. And here you throw in some sulfuric acid, catalyst, and water. So if you took this alkene and you threw in some sulfuric acid, a couple drops, and water, you would make an alcohol. So here, the first thing that happens is the acid's going to protonate. Okay, that's the first thing that's going to happen. Acids are strong, they happen quick, they happen fast. And now that means a hydrogen, because that's what an acid gives, goes to one of these carbons, and the other carbon is going to become a positive charge. So this one's making a carbocation, so you can expect this reaction to be regioselective, Markovnikov addition. Okay, it's going to be the more stable carbocation, and then the OH will come in. That's when your OH will come in as a nucleophile and add. And what does that look like? So you get your OH, and this is going to then deprotonate. So then your HSO4 will deprotonate to make the alcohol. This is a good example because now we have an unsymmetrical alkene. So when the acid adds, first step, step 1, you protonate it and make the carbocation. So you're going to get the H is going to add to this carbon, the proton source, the strong acid, and this carbon is going to get the tertiary carbocation. And then the nucleophile that adds is the water. And this adds, and that's how you get this alcohol. And this is a Markovnikov, Mark's alcohol, okay? Because you get the more substituted carbocation. The OH adds the more substituted. And this is showing you the mechanism here. The first thing you do is protonate. Now H2SO4 is the same thing as writing H plus or H3O plus. So in the mechanism, they're just showing you this is like taking some generic acid, H3O plus. You protonated, you get your carbocation. This is going to be Markovnikov's rule, okay, Mark's rule. And then the water is your nucleophile that adds in step 2. So this is stepwise, so you can expect the reaction energy diagram to look like this with a carbocation intermediate. And then you just deprotonate to generate your functional group. So here we can also add methanol, right? So the first thing, we don't just have to add water, and we can add methanol. And so the acid is going to protonate there, and you're going to get a carbocation on the more substituted tertiary carbon, carbocation. And now your nucleophile is going to be the oxygen of methanol. And so this is step 2. You get OCH3. You do still have that proton there, so then HSO4 is going to regenerate its acid by doing a deprotonation step to make, and this is a functional group called an ether. Okay, the other step, the second way to make an alcohol is hydroboration oxidation. And so you might want to take this BH3, which is one of your reagents, and split it up like this, HBH2. Okay, and so the first thing you're going to have is one of the carbons is going to get the H, and the other carbon of the carbon-carbon double bond is going to get the BH2. So BH3 is going to do an electrophilic addition across the double bond. This is going to be step 1. So step 1, you got to add BH3. Okay, this is hydroboration. You're adding a hydrogen and you're adding a boron. Hydroboration. Now, then you've got to write step 2. Otherwise, it's assumed across the reagent reaction arrow that you're adding at the same time. It doesn't work. So you basically add this, maybe go to lunch, maybe go read your email, go do something for an hour, and then once you make your alkyl borane, so you would do a little test, you take an aliquot and test it, then you would do an oxidation. And in the oxidation, you don't have to do electron flow arrows. Hydrogen peroxide. You'll have a solution of hydrogen peroxide and probably some sodium hydroxide solution, and then you're going to drop it in here, and all that's going to do is it's going to replace your BH2. You can think of BH2 as a placeholder with OH. And since this is an oxidation reaction, do you remember Leo Gur? Leo Gur, the loss of electrons, gain of electrons. We don't do this nucleophile electrophile curved arrow to denote that. We just do a replacement. Okay. Now, not only is this regioselective, you're going to find that it's concerted, and that means this is going to be syn addition. Okay, so that means the H and the OH are going to add the same side. Okay, so that means you're going to have both dashes or both wedges. And that's how you do syn addition. So you're going to have some dashes or wedges. That's stereo specific. And it's regioselective because the BH2, which you can't tell here, is going to add to the least substituted carbon. So this is your first time you're going to see an anti-mark. This is an anti-mark reaction. So regioselectivity, it's anti-mark. Stereoselectivity, it's syn addition. So this is anti-mark syn addition. So here we have a symmetrical alkene. Both of these are symmetrical alkenes, so you're not going to see the difference there. But what they're showing you is these are added on the same side. So you might want to make this both a dash or both a wedge. And then the BH2, so you can, is going to get replaced with an OH. And you need to show this either dashes or wedges. Here, step 1, you're going to have a BH2 adding onto one of the carbons, hydrogen on the other, and then it gets replaced in step 2. They're showing you that usually when you buy this, the BH3 is complex with THF, so your bottle that you get is BH3 with this dot THF, tetrahydrofuran. It stabilizes it so it doesn't catch fire. Okay, these things can catch fire. They're not very stable, but the THF does this Lewis acid, Lewis base complex. We call that a complex, and it stabilizes it so you can just put it in there. Yeah. So here they're showing you that the first step, the hydroboration, so this needs to have a 1. You're adding the H and the BH2 across the pi bond, electrophilic addition. Now we're talking the mechanism here. So you can see it adds the same side. So this is your mechanism. I do expect you to be able to draw this mechanism where this bond here is going to make a bond here. So that's what this is right here. And then this bond here is going to make a bond there, and that is what this is. And this is happening at the same time. This is concerted. It has to be concerted if you're going to have syn addition. You can make this both wedges, and I need to see that. I need you to do that. Both wedges or both dashes, you get to choose. But when you make them like that, then you know that they're syn addition. And then so after step 1, then they're just showing you you can do this multiple times, not a worry here. They're showing you to prevent that from happening. A lot of times you can buy different derivatized, alkyl derivatized alkenes, so then it can just add 1 hydrogen. This is important for anti-mark. So this is showing you that's anti-mark, and that means this reagent, step 1, hydrogen and BH2 are going to add to the carbon. And so we have 2 carbons to choose from of the double bond, and BH2 is going to add to the least substituted. It's a steric thing. Okay, considering steric factors. So the BH2 is going to add to the least substituted carbon, whereas the hydrogen is going to add to the more substituted. This is the only product. Okay, this is not formed. There could also be some electronic factors that talk about this. I just usually just say, let's just focus on sterics. Okay, so here they're showing you the preferred product here, and then the thing is, when the second step, when you add hydrogen peroxide and a sodium hydroxide mixture, all you got to do then is just replace the BH2 with OH. So then you just go like that. And so what I want to see is this either all dashes or all wedges. So, and then this is also maintained. And that will capture your cis or your trans, not trans, cis concerted stereochemistry, which is syn, in this case syn. And that's what they're talking about. When you oxidize it, step 2, retention of configuration. That means if you have a wedge here, it stays a wedge. And by you showing that with dashes and wedges, I know that this reaction, hydroboration, is syn addition, and you also know that it's anti-Markovnikov by putting the OH on the least substituted carbon. So the addition of hydrogen occurs in one step. No rearrangements can occur. Okay, that's important because you don't get a carbocation. No carbocation. The OH group goes to the less substituted carbon. This is syn addition. So show me both dashes. You get to choose, or both wedges. This is an example of making the anti-malaria drug here, and we have an alkene, and they wanted the anti-mark alcohol, and so here the intermediate here to draw this molecule synthesized in the lab. That was the double bond. The BH2 goes there, and then H2 would, or just H would go there. And then the second step, see how we have 1 and 2? And then number 2, you add hydrogen peroxide and some probably sodium hydroxide. This BH2 gets replaced with an OH, and that's anti-mark. And then there's other steps there. Okay, so that was that example. Now what if you just add a halogen? Okay, so we're talking ClCl or BrBr. This is anti-addition. Okay, so you need to know that that's anti-addition. How are you going to show that? You're going to show the halogen adding like this diaxial. Okay, so you'll show that. Or you could show it, one is a dash and one is a wedge. That would show anti. So why does it do that? Well, that's in the intermediate. So what I do want to see is the reaction mechanism. So here the double bond will attack the Cl, and the Cl leaves, okay? But what it does is it makes this three-membered ring, okay? And this is a three-membered ring, and this would be called a chloroneum, okay? The bromine here, intermediate, and you can make it like this. You get to choose dashes or wedges. Notice I have a positive charge on the bromine. This is called a bromonium ring, okay? The reason why these are so big and they're sharing, now both carbons are sharing the Cl. You see both carbons make, this is their intermediate. Both here, both carbons are sharing the bromonium. And then what happened, right? So this added there, this left, because this kind of does this polarized induced dipole. Now we have this nucleophile in solution, and it's going to do a ring opening, and it's going to come in SN2 fashion. Okay, so it's going to come and open that. And so then what you need to do is, this came from underneath, this is above. And so if this came from underneath and this came above, you're capturing that anti-addition. This opening, ring opening, is an SN2 fashion. You saw this in the epoxides. So you've seen the three-membered rings where, and notice the epoxide, when the oxygen had a positive charge, it was sterically, actually electronically driven. So in this case, the more substituted carbon has more of a more stable delta positive, like a carbocation like, and so your nucleophile will come in and will come into the more substituted carbon. And so that's what this is showing you here. Um, they're polarizable, so that's why it has this induced dipole, the electron deficient, electron rich. So this is why it adds. There's no rearrangements to occur because you make your halonium intermediate, which is that three-membered ring with the positive charge. And you get only anti-addition, and that's because the other halogen will do a ring opening. And the ring opening has to have backside attack. So this suggests that carbocations are not the intermediates. This is how they know. Scientists who study addition of the X2, this is just showing you that it makes this bridged halonium ion, and then your nucleophile will do the ring opening. And that's how you get this anti-addition. Carbocations are unstable because they only have 6 electrons. So this is why you get rearrangements whenever you have this, and this is unstable. But here, this is this has ankle strain, so it's going to go ring opening, but it's it blocks. There's no rearrangements. There's no rearrangements here. So this is an important intermediate to be able to draw. So you can have them above or below. You get to choose. Just pick one though to show the stereo selective, and then the chloride can come in here and do that ring opening, and then you would want to have draw your product in to capture that with this going up and this going below. You see the dashes and the wedges, and that's what this is showing you. I only require you to show one, but you might have a standardized exam that you have to pick both the enantiomers. I'm okay with you just picking one. You can choose if you want to be a wedge person or a dash person, but because you draw this intermediate with the wedges or the dashes, then I know that this is a stereoselective SYN, not SYN, but anti-addition. All right, so they're just showing you here that what's the relationship once you make these. You can take an achiral compound and you can make a chiral compound, but it's going to be racemic. It'll have R and S, 50%. This is identical because there's a plane of symmetry. Halohydrin formation. Now, first thing we do is we make that bridged intermediate. So we're going to make that halonium three-membered ring, and then we're going to introduce a different nucleophile. And you can do this by just adding a little bit, like if you add a little bit of bromine, and you don't have any water yet, you just add that bromine, and then it forms this bridged three-membered ring. Okay, so then you make that with the bromine, and then later you might go to lunch, and then you come in and you add water. But you'd have to do this dropwise. You'd have to add the bromine dropwise, and then this will open, and let's see how you get, well, to be consistent, let's go after this one, this carbon, this opens, and so I would be fine with you drawing it like this, but this is anti-addition, and now you're going to be able to notice, I will be able to notice, this OH here, they're symmetrical, but this nucleophile is going to add to the more substituted delta positive carbon of the three-membered ring. Okay, here chlorine, this one's going to add chlorine to one of the carbons, and then water, the OH, we'll add to the other one. This is a chlorohydrin. So this is a halohydrin. So it can be the bromine, or a Cl is your halogen. Hydrin is always OH. The OH is going to add to the more substituted carbon, and there's no rearrangement. Okay, so this is showing you make your halonium atom an ion intermediate, and then water is going to do the opening, and then you get deprotonation. Okay, so this one, you don't have to know that. We're not going to talk about that right now. Okay, so here, bromine, you're going to make your bromonium intermediate. You might want to draw this out. And then the water is going to HOH, the water nucleophile, then we'll add. And I'm happy with you just showing one of these. You don't have to show all of them. But this is why you get to the transenantiomers. Okay, now we're dealing with an unsymmetrical. So now watch this first step here. You're going to make your bromonium. So there we have this. And let's draw that bromonium. And we can do wedges. And that has a positive charge. Okay. And so now water is going to come in. Now water is going to come into the more substituted delta positive carbon, more stabilizing, and it's going to come in backside attack. So then what I want you to draw is this comes in OH, and then this is Br. So this comes in underneath there, and that goes that way. And so you see that this is the only product. This is a tertiary alcohol. See that carbon bonded to the OH, it's bonded to 3 carbons. That's a tertiary alcohol. This is this is a tertiary. So we drew the same thing. This is a primary alcohol, not formed. This is the mechanism that we just drew. And you can see that the OH is going to attack the more substituted carbon. So this mechanism is a 3-step. You got to make the bridged halonium ion. There's no rearrangements that occur because of this bridged halonium ion. And then the nucleophile is going to attack the the more substituted carbon, actually, and you get anti-addition. This is just showing you a synthetic reaction in which a estrone, which is birth control, they need a chlorohydrin intermediate here. So here chlorine and water is added here to get the chlorohydrin. So now we're getting into where we can do lots of different reactions, and then we can do multi-step synthesis, which you're going to get in your exams. And this means like step 1, 2, and 3. And so you want to do 1 first, and then 2, and then 3. And when you get a lot of these, the first thing you want to do is this acidic or basic? Where's the nucleophile, electrophile, or is it oxidizing, reducing? And so you want to be able to classify these different reactions because they're going to guide you in your problem solving. So here you have a starting material, alcohol, and what reactants do you need to make this product? And this is a dihalogen. So then you want to think, okay, this is a retrosynthetic arrow. So you're learning that these different arrows, it's a sad looking one, but it's this block arrow like this, and it means retrosynthesis. And it means, what is the starting material for this? So hopefully you know that the starting material would be an alkene, right? And then in order to get that, bromine was, so this is a halogenation reaction. But how do you get from the alcohol, how do you then go to the alcohol? How do you do that from the alkene? Um, so how do you, which is, this is your step here from the alcohol to the alkene, that's a dehydration. So sulfuric acid and heat would do that. So how do you go forward? Well, you want to think backwards. See, you want to work backwards, and that's this retrosynthesis arrow here. That's thinking backwards. So thinking backwards, this is an alkene. Thinking forward here is how to go from an alcohol to an alkene. So here, now you know a few things. You can do this halogenation with bromine on the alkene, and you know how to get to an alkene through an alcohol through dehydration. So then this is step one, and then this is step two to get you this. And so you might see this written, you take an alcohol, you'd say, okay, 1, sulfuric acid, and then 2, bromine. What is your product there? You would step 1 and go, okay, that's an alcohol, and then step 2 would be the halogenation. And I'd want you to do a dash and a wedge to show that these are anti. That's what I would want to see. And that wraps up these electrophilic additions. Like I said, I'll do the other one where we can include the oxymercuration demercuration reaction.